Today we're going to talk about the defining characteristics of R, the real number system, that distinguishes it from all the other number systems. But first, let's talk about why we want to know the defining characteristics of R. I mean, it seems like a really pointless thing to learn. Well, while the characteristics of R itself isn't really applicable, learning it will give a stronger understanding of calculus, which is applicable. More specifically, it'll help build the foundations of analysis, which is a rigorous study of calculus, or basically it's calculus rediscovered from scratch. So if you decide to forget everything about calculus and build it back up from scratch, what would it be like? Calculus, at least Calc 1 and 2, has its foundations in the real numbers, so really understanding the real numbers will give a stronger foundation when trying to understand something like calculus or analysis. Moreover, I just think it's a pretty interesting topic, since we've all learned about the real numbers since elementary school. It's like an old friend of ours. But we haven't really learned what characteristics makes it so unique. So I think it's a good time to maybe get to know that old friend a bit better. Okay, so let's take a look at the outline of the three characteristics of R. The first characteristic is the field properties. The second characteristic is the order properties. And the third is the axiom of completeness, or the completeness property. Now, any one of these characteristics taken alone doesn't distinguish R from the rest of the number systems, but if you take all three characteristics as a whole, it does distinguish R from all the other number systems. I think the best way to think about it is to think of these three characteristics as a three-layered sieve. So think of each characteristic as a sieve where if you pass a number system through it, if that number system satisfies that characteristic, then it passes through, no problem. However, if the characteristic isn't satisfied, then the number system gets filtered out. So if you pass all of the number system through this three-layered sieve, the three characteristics, the only one that doesn't get filtered out is R, meaning that R is the only number system satisfying all three characteristics. First, let's take a look at the field and order properties. These two I feel aren't very interesting, so we'll just take a short look at it and then move on. Typically, in an analysis course, you learn about these things called field axioms, which define a field, and also some order properties that define an ordered set and an ordered field. But right now, I think it'd be more beneficial to take an informal high-level overview of these two, and then we'll move on to focus more on the axiom of completeness, which I think is the more interesting of the bunch. So the field properties basically state that you can add, subtract, multiply, and divide real numbers. Seems pretty obvious, but let's take a look at some number systems that do get filtered out by this first sieve. First prime candidate? Well, the natural numbers. You can't really subtract in those. The reason? Well, it's because there aren't any negative numbers yet. So if you subtract certain natural numbers, like you take 1 minus 2, you'd get negative 1, which is an answer that doesn't exist in the natural number since it's a negative number. We don't really like this, so we just say that you can't subtract natural numbers until you add the concept of negative numbers to the mix. Next one that gets filtered out? Well, that'd be the integers. You can't really divide those, similar reasoning as before. You take 1 divided by 2, you get 1/2, which is a fraction. That's a rational number and not an integer. So until you add the concept of fractions to the mix, you can't really divide. So right off the bat, these two number systems already get filtered out. Next, let's take a look at the order properties. This one just basically states that you can compare real numbers. So if you have some sense of less than, equal to, and greater than, then you've pretty much satisfied this property. And that's pretty much it. Super simple. And you might think that no number system could possibly be so stupid as to get screened out by this sieve. But if you're thinking that, then recall that there's the complex numbers. I mean, there's a pretty good reason why you don't hear people say that 1 plus I is greater than I. Yeah, because there's no order property in the complex numbers. But the proof of that is a whole other topic. Finally, we get to the axiom of completeness, the core of this video. If we take a look at what's currently still left after the first two sieves, that'd be the rational numbers. So our question now is what exactly it is that distinguishes R from Q, the set of all rational numbers. This has to do with the idea of completeness. To gain a better understanding, let's first see what it means to not be complete. Recall that back when you first learned about the rational numbers, you probably learned that if you plot all the rational numbers on a number line, you'll have some gaps or holes in the line. For example, square root of 2 is a super well-known hole, and pi is yet another well-known gap in the rational numbers. These are both irrational numbers, meaning that they can't be written as a fraction, so it's not a rational number. So what does it mean to not be complete? That would be to have gaps or holes. And it's the filling in of these gaps that makes the real numbers complete. And the axiom of completeness makes that definition more precise. But before we can understand the axiom of completeness, we need to first understand the idea of an upper bound and a least upper bound. An upper bound of a set S is a number m that is greater than or equal to all elements of S. That should feel pretty intuitive, but also note that any number greater than an upper bound must also be an upper bound. So that just means there could be more than one upper bound. What about the least upper bound? Well, the least upper bound is, as its name suggests, the least of all the upper bounds. So let's say that you have a list of all the upper bounds, then the minimum of that would be the least upper bound. Formally speaking, a least upper bound of a set S, it's also called the supremum of S, or sup S, has two properties. One, it has to be an upper bound. This one's pretty obvious since it's in the name. And two, for all upper bounds m of a set S, the supremum must be less than or equal to m. This is just basically stating the least part of the least upper bound, which means that it's got to be the minimum of all the upper bounds. But also note that the second property implies that any number less than the supremum is not an upper bound, because if it were, then that number would be the supremum instead. And also note that it also implies that any number greater than the supremum of S is not the least upper bound. It's just an ordinary upper bound. Now let's get into the formal statement of the axiom of completeness. The axiom of completeness states that if S is a non-empty set of real numbers that is bounded above, then the supremum of S exists and is a real number. So the set has to be non-empty because you can't have a least upper bound for nothing. It's also got to be bounded above because you have to have at least one upper bound to have a least upper bound at all. As an example, let's take the open interval between negative square root 2 and square root 2. It's definitely not empty. It's also bounded above since the interval ends at square root 2. By the axiom of completeness, it must have a least upper bound, and that least upper bound must be a real number. So in this case, square root 2 is clearly the least upper bound, and so we conclude that square root 2 is the real number, if we consider the set of all real numbers. Also note that the least upper bound hugs tightly to the end of the interval. This will be important when trying to construct R from Q, which also happens to be a very long proof, so it won't be covered in this video. Also keep in mind that if we choose to stay in the rational number system, we wouldn't have a least upper bound in this case. Since the least upper bound is square root 2, and it's not rational, and we know that any number less than the least upper bound isn't an upper bound, and we also know that any number that's greater than the least upper bound is not the least upper bound. It's just an ordinary upper bound. So we see in this case that the least upper bound doesn't always exist in the rational number system. So the axiom of completeness doesn't apply for Q, and thus this axiom filters out the rational numbers, and we're finally left with only the real numbers. Finally, we'll talk about why the axiom of completeness implies that there are no gaps or holes. We'll first assume that there are gaps and holes. Then all we have to do is choose an interval that ends at a hole. So clearly the hole must be the least upper bound of the interval. So by the axiom of completeness, that hole has to be a real number. So what that basically means is that there aren't any holes at all, since the number corresponding to the hole itself is a real number, so we've basically filled in the hole with a real number. And in fact, this allows us to represent each real number in a different way. A real number R can be represented as the interval or set of rational numbers less than or equal to R. So basically, each real number can be represented as a set of rational numbers ending at the hole. Each of these sets is called a Dedekind cut. So this is a method of representing the real numbers as a cut, and it might seem a bit contrived, but it forms one of the key methods of constructing the real numbers from the rational numbers. But that's a topic for another day. In conclusion, the real numbers must satisfy the three properties of 1. The field properties, 2. The order properties, and 3. The completeness property defined by the axiom of completeness. Thank you for watching, and I hope you learned something new today.